We'll just wait for a few more minutes to see if anybody else joins in. Okay, let's begin. Hello, everyone. This is Tanya. I'm one of the TAs assigned to the course Aircraft Design taught by Professor A.K. Ghosh. So we'll be going over the questions of week 5 and then some of the contents of week 4 and some of the contents of week 5 to help you solve the assignment. So let's start. So in what flight regime is wave drag negligible? What is wave drag? What is wave drag? drag in supersonic conditions when the shock wave occurs? So the answer to this question would be is negligible in subsonic flight. So yes, so the wave drag occurs due to the shock wave formation and then the turbulence thereafter, like beyond the shock wave. And then there's a flow separation and there's turbulence that causes drag. So wave drag occurs due to the formation of shock wave, which happens in, you're right, supersonic conditions, transonic to supersonic conditions, and beyond that. We had seen this, I think, in the last class. What are the primary causes of wave drag? We just discussed this. So it's the formation of shock waves around an object moving at transonic or supersonic speeds. Right? All of those reasons are causes of drags, but the cause of wave drag is the formation of shock wave. So interaction of the aircraft with air molecules at high altitudes, the general cause for drag. Friction between the aircraft surface and surrounding air, similar to the first option. Vortices shed from the aircraft's wing during flight. So what kind of drag was that? The last option. Vortices shed from the aircraft's wing during flight. What kind of drag did that create? Induced drag, correct. So this produced induced drag. All right. Next question. What is meant by, it should have been what is meant by drag divergence Mach number, not higher divergence Mach number. What is meant by divergence Mach number? We had again seen this. So which is the right answer? So it's basically when the Mach number has an exponential increase, right? So that happens when there's a shock wave formation. So the Mach number at which shock waves begin to form on the wings. That is divergence Mach number. Okay. Supercritical airfoil is primarily used for, again, something that we've seen extensively. So supercritical airfoil has a flattened upper surface. It's a cambered airfoil with a flattened upper surface. What happens is that it delays the formation of the shock wave. Delays the formation both in terms of Mach number and in terms of the location of so this is the typical cambered airfoil, right? So a supercritical airfoil would have a more flattened surface. So in your typical case, your shock wave might have formed here, but in a supercritical airfoil, it forms aft. So it delays the formation of the shock wave. So it's primarily used for higher divergence Mach number, right? Because we just saw what is divergence Mach number. It's the Mach number at which the shock wave begins to form. It's that. Yeah, so this was a slide from one of the previous sessions. So we'd seen the advantages of supercritical airfoil. So it higher drag divergence Mach number. Shock wave forms aft when compared to a conventional airfoil, compared to typical cambered airfoil. And so you have reduced boundary layer and shock interaction, and hence less drag, right? So it's delayed. So there's a lesser interaction and hence lesser drag. So it also leads to a thicker wing, and we'd seen how the thicker wing implies that it's a lighter wing, right? You need less structural reinforcements. So it's a lighter wing. Okay. The techniques employed to delay the critical Mach number of an aircraft are. So all of these techniques are in some way or the other to reduce the drag. Okay. So all of these, sweeping the wings backward, increasing the camber of the airfoil, adding winglets to the wingtips, all of them reduce the drag, right? So it is all of them. Correct? So this is just, I think, yeah. So this is how the sweep angle, swept back wing gives you a lesser normal velocity, right? So if it did not have a sweep, your incoming velocity and the normal velocity both would be the same. So V infinity, right? What the surface of the wing sees would be V infinity. But because there is a sweep back angle, this V infinity is reduced by some quantity. It's reduced by cos of the angle, cos of the sweep, right? Cos of this angle. So your actual velocity incoming V infinity is reduced by this cos component, which gives you a reduction in the normal reduction in the velocity that the normal component sees. So reduction in the velocity that the airfoil sees. Okay, and hence it reduces the critical Mach number. This is how sweep was reducing. Then, how does wing sweep affect drag? Which is the right answer? Wing sweep, how does it affect drag? Decreases the induced drag, right? Yes, wing sweep decreases the induced drag. How do you try to justify that? So induced drag happens due to the wingtip vortices, right? That is reduced in wing sweep because the flow above and below the surface of the wing are interacting towards the tip in a more gradual fashion. It's not very drastic. So the wingtip vortices are not very strong. They're weak vortices. And hence the induced drag is reduced. Similarly, what about the wing twist? Wing twist, I think we've seen this in the last session as wash out or wash in. So it's a similar thing, that the root angle of attack of the wing is different from the tip. That is your wing twist. Similar to the wing sweep, this also has a decreased induced drag. Why? Why does it have a decreased induced drag? Try justifying it using the same reason as the wing sweep. Low vortices. Why low vortices? Because again, the interaction between the upper and the lower surface, the flow of interaction between the upper and the lower surface of the wing is more gradual in the case of a wing twist. Right? It builds up a profile. So it is more gradual. So that is why the wingtip vortices are lesser and hence the induced drag is reduced. So that's that. What role does camber play in wing design? Which of the following is or are correct? Camber increases the lift, decreases the drag. This is anyways true. So if this was your symmetric airfoil and this was your cambered airfoil, for the same angle of attack, you get a higher lift in the case of cambered. This is cambered, this is symmetric. CL versus alpha. Okay, so you have for the same angle of attack, you get a higher lift in the case of camber. And okay, A and D, correct. So it influences the stall characteristics. In the same graph, you can see that the stall angle is reduced in the case of cambered airfoil when compared to symmetric airfoil. So it does have an effect on the stall characteristics. So both A and D are correct. How does drag divergence Mach number relate to critical Mach number? We've seen this graph. It's something like this, right? Where this is the critical Mach number. This is your drag divergence Mach number. So drag divergence Mach number is greater than critical Mach number. Correct? Yes. So this was the graph. Your critical Mach number is here and drag divergence Mach number is here. So it is higher than the critical Mach number. Drag divergence Mach number is higher. Okay. How does thickness to chord ratio affect the wing performance? So this is a slightly ambiguous question because we had seen one of the graphs that sir discussed in the class, which was CL versus thickness to chord, and it followed a pattern like this. So up to this region, when you increase the thickness to chord ratio, there we see an increase in the lift. But beyond that, it follows the reverse characteristics. Okay. So this was slightly ambiguous. It should have been up to that limit. Then A would be right and vice versa, right? A and B are effectively the same sentences. So this was slightly ambiguous, but it's both A and B. Now, this was a question that we had seen multiple times in the last 2 weeks, but nobody really came up with answers. I'll just discuss this. We've been delaying this for a while now. When the angle of attack decreases, the moment of center of pressure will be towards the trailing edge. This was the right answer. And I'd asked for justifications as to why this was true. So let's just have a look at that. So they show you three different angles of attack witnessed by the same airfoil. So one is at 4 plus 4 degrees, one is at -8, and one is at +10. So when it is at +4, you see the pressure profile, right? Above it is negative pressure, below it is positive. And when you reduce the angle of attack, you see that the entire pressure concentration moves towards the trailing edge. So the center of mass or center of the distribution of pressure would move towards the trailing edge. When you increase the angle of attack, the entire pressure profile, the center of the pressure profile is shifted towards the leading edge. When you decrease the angle of attack, it moves backward. It moves towards the trailing edge. Okay. So it's just the center of the entire pressure distribution moves ahead and behind. So the question was when you reduce the angle of attack, it moves towards trailing edge. Okay. So these are just the graphs that show you the same pressure distribution. So it's uniform pressure distribution over a symmetric airfoil at 0 degrees angle of attack. When you increase it, you see the pressure profile. It moves towards the leading edge. There's a distribution moves towards the leading edge. And this was just an animation that I thought was beautifully done. So we'll just look at it. It shows you 4 different values. Just try to understand which of those 4 values, like just see if you can find out which one they're showing. Okay, the first one was, what was this? What was it showing? The colors? What we just discussed, right? It's the pressure profile. Red is positive and blue is negative. It's the pressure profile, right? So now if we go to the next, now let's see the next one. Next animation. What did that represent? This one, what do you think it represented? It was a net normal force, okay? Net normal force acting on the airfoil. Now let's look at the next one. This is the next animation. What was that? What was this? What did it represent? It's similar to the net normal force. It's almost similar to the net normal force. What is this value that's being represented here? That's being plotted here. Let's try to think about it. I just thought it was a beautiful animation and I thought I should share it. Lift, exactly. So it's perpendicular to the oncoming velocity. It is the lift distribution. Now let's look at the fourth one. Yeah, this one. What is this? What do you think that was? Drag, correct. The previous one was lift and this is drag. So throughout this animation, there is something missing. There's something that's wrong, some error. What do you think it is? Especially in the first one. Can you try and tell me what you think is missing, what's wrong in this animation? What's missing? What is wrong? A very interesting animation, but there's something which is not correct here, some error here. In reality, if you were to keep an airfoil in a flow and plot it and visualize it, what would be different? This is an animation, this is not a real experiment. So in an actual experiment, what do you think would be different? Yeah, so at trailing edge, there would be a flow separation, right? So you would have, what do I say? There would be a possible flow separation here, and there would be vortices, correct? So that is not seen here. So this is a completely laminar flow throughout. So the turbulence or the flow separation, the boundary layer interaction, that is not shown here. So that is the one thing that I found. But otherwise, it's a very interesting animation. Okay, let's move on. Okay. During a flight, if the aileron is deflected with a certain positive angle, how will this affect the lateral stability of an aircraft? What do you think is the answer? During a flight, if the aileron is deflected with a certain positive angle, how will this affect the lateral stability of an aircraft? Okay, let's just try thinking about it. During the flight, if some aileron's something that we are not very familiar with, so if if an elevator is deflected with a certain positive angle, how will it affect longitudinal stability? So longitudinal stability is something that we have dealt with, right? In the stability control course, we have studied this extensively. So if that is more familiar to you, you can just tell me how during a flight, if I deflect the elevator with a certain positive angle, how will the longitudinal stability of the aircraft be affected? Okay. So aircraft will pitch down. If I deflect the elevator down, aircraft will pitch down. How is the stability affected? What will be the effect on stability, longitudinal stability? Why would it be more stable? Can you try and explain? Okay. So if I am flying, if this is this is the fuselage reference line and this is oncoming velocity v infinity, this is my equilibrium point, right? And then I deflect my elevator down. There is a lift force, and then the airplane pitches down, right? So if I deflect the elevator down, the airplane pitches down. So how is it returning to its equilibrium position? Try and think about it. So how do we define stability? Longitudinal stability. How do we define it? Static stability, longitudinal static stability. Okay, what is the definition of a stability? Like, you don't have to name it in the exact terms, just what you understand by it. slope of CM alpha. So this is your CM versus alpha. And should it be positive or negative? Slope of CM alpha should be positive or negative? Yeah. Tendency to return to its equilibrium position, negative slope. Correct. All this is true. So when I deflect the elevator, how is this tendency affected? I deflect the elevator, the aircraft pitches down. How is the tendency to return to equilibrium position affected? So what is the effect of the elevator on this CM alpha? CM alpha slope should be negative. Now if I deflect the elevator, how does the CM alpha curve change? Does it become more negative, less negative? And why does it become whatever? You're right. It is the tendency to return to its equilibrium position. You're right about the CM alpha slope being negative. Both of them are right. Now, what is the effect of elevator on this? Just think about it or go over your notes or, Google it or whatever and just think about it. How does the elevator affect this? Think about it. So to get stability, what do we do for the aircraft to be longitudinally stable? What do we do? What part of the aircraft contributes towards the stability? Just think about it. So your aircraft is flying. This is the equilibrium condition, fuselage reference line. Then there is a gust and the angle of attack is changed. It becomes this. Now you need to bring it back, right? You need to pitch down. What part of the aircraft brings it down? What part of the aircraft or what structure on the aircraft makes this tendency to come back to equilibrium? Horizontal tail, exactly. So there is a tail here which produces the restoring moment. So tail contributes towards this restoring moment, right? So now think about it. What does the elevator do? So if I change my distance from, like if I place my tail further away from CG, my slope changes, CM alpha slope changes, right? Now tell me, what does the elevator do? Which pin have been here? The tail here, which produces the restoring moment. Yeah. So tail produces the moment about okay, when deflected. Elevator produces moment about CG when deflected. Okay. So does that change the CM alpha slope? No. So when you deflect the control surfaces, they do not affect the stability in any way. Okay. So deflection of any control surface does not affect the stability, lateral, directional, longitudinal. doesn't affect stability in any way. Control surfaces are for you to control your aircraft. When you want to pitch up, when you want to pitch down, you deflect your elevator. When you want to roll, you deflect your ailerons, right? But the control surfaces do not contribute to stability. There is the inherent tendency to go back to equilibrium position when it is subject to disturbance is stability. Control surfaces have nothing to do with stability. It does not change that slope, right? Only the position of your tail from the CG changes the Cm alpha slope. The deflection of any of the control surfaces have nothing to do with stability. So the answer here would be unchanged, right? Deflection of any control surface does not change stability. Please keep that in mind, okay? So the only thing that changes stability is the slope of Cm alpha. You were right about that. And that comes from where? The location of your tail, okay? Yeah. So aileron control effectiveness depends upon it's similar to one of the questions that you have. Aileron is on which of the surfaces or which of the structures of an aircraft? Wing, correct. So it depends upon the lift curve slope of the wing. So for the vertical tail, what is it for the vertical tail? Rudder. And horizontal tail, so this is rudder. Horizontal tail is elevate, correct. So lift curve slope of the wing is what the aileron control effectiveness depends upon. Okay. The primary control for adverse yaw recovery is, what is adverse yaw? Is adverse yaw? Yaw due to some gust? No, no. So that is called side slip, right? Yaw, or when there's a sidewards gust, you have side slip angle, beta. Rolling and yawing, yes. So can you try and explain that further? Why is it called adverse yaw? You are right. So it is the coupled motion, so rolling and yawing. But why is it adverse yaw? Can you explain a little more? Rolling, just take an example, rolling in one direction. Okay. When we roll, we get a yaw motion due to different lift on the wing. So adverse yaw is because when we try to roll right, it has a yaw in the opposite direction, right? So you're right. The reason is right. When we roll, we get a yaw motion due to different lift on the wing. Correct. So that is adverse yaw. I think I have a video that will maybe clear this. So what is the primary control for adverse yaw recovery? So when you roll right, you also want to yaw right. So what is the primary control for that? Rudder, correct. Okay, so there is a video here. Let's just try.
An aeroplane in straight and level flight has a lift.
Tell me if you can hear the audio. Okay, so let's just listen to this.
An aeroplane in straight and level flight has a lift distribution pattern that looks something like this. The lift generated by one wing is the same as the lift generated by the other wing. Deflecting the right aileron down causes an effective increase in the wing's camber and an increase in the effective angle of attack. The lift from that section of the wing increases. Deflecting the left aileron up causes an effective decrease in the wing's camber and a decrease in the effective angle of attack. The lift from that section of the wing reduces. The primary effect of aileron deflections is a roll. This is an approximate drag distribution pattern. When the ailerons are deflected, extra drag is generated by both wings. However, more drag is generated by the downgoing aileron than the upgoing aileron. This is induced drag, and it is caused by more lift required on the right wing to help initiate the roll. Combining the lift and drag effects together creates the undesirable tendency for the aeroplane to roll in one direction, but yaw in the opposite direction. This effect is called adverse yaw.
Is that clear now? So it's not just because of the differential lift distribution. It's differential lift distribution coupled with the fact that there's a differential drag distribution on the aircrafts, and they are in the opposing fashions, right? So it rolls in one direction and yaws in the other direction. So that is why it's called adverse yaw. Okay, so now let's just look at it.
This effect is most noticeable at low speeds and on aeroplanes with high aspect ratio wings. There is another reason for the adverse yaw that is not often mentioned. In straight and level flight, both wings encounter the relative airflow head-on. But as the aeroplane rolls and the left wing moves down, a small amount of additional airflow strikes the wing from below. As the right wing moves up, a small amount of airflow strikes the wing from above, and vice versa. So as the aeroplane rolls, the relative airflow is deflected slightly up on the right wing, and the relative airflow is deflected slightly down on the left wing. As lift always acts at right angles to the relative airflow, the upward deflection of the relative airflow on the right wing causes lift to deflect backward. Conversely, as the left wing goes down, its relative airflow is deflected downward and its lift is deflected forward. The slight deflection of both lift vectors results in an adverse yaw moment to the right. The adverse yaw moment is felt when the aeroplane is rolling, and it stops when the aeroplane stops rolling. Adverse yaw can be prevented by using the rudder to create a yawing moment.
Do you see the two reasons, two causes of adverse yaw? So first one was due to the differential lift and the drag distribution on the right and the left wing. Okay, and they were working in opposite fashions. The second reason was that so one lift, one wing is going down, one wing is going above, and so there is a change in the lift angle. And then again, that is differential and it produces a yaw motion in the opposite direction. So there are two reasons for adverse yaw. Okay. Now let's see how to overcome this.
Adverse yaw can be prevented by using the rudder to create a yawing moment that helps to turn the aeroplane in the correct direction to remain coordinated. Some aeroplanes incorporate design features to minimize the adverse yaw. One such feature is called differential ailerons. By excessively deflecting the upward aileron, drag is increased on the downgoing wing. This produces a desired yaw force in the direction of the turn.
So I hope the concept of adverse yaw is now clear, and how it's produced and how to overcome it, right? I thought it was a very interesting video. Okay, now this should help you solve the questions of week 5. So let's just go over the concepts of directional stability and lateral stability. Okay, so before that, we'll start with the conventions. So for directional stability, the convention is right wing going back is a positive yawing moment. Okay, so right wing going back. Why do you think that is a positive yawing moment? Why is that the convention? So when you have your aircraft, you have your wing here. Bear with my drawing. So you have your positive x-axis, positive y-axis, and this is your positive z-axis. So yawing moment occurs about the z-axis. So right wing going back, why is it the positive yawing moment? The right hand thumb rule, right? So you put your thumb along the z-axis and the direction of the curl of the fingers is the positive moment. So in this case, the right wing going back, or when you see from above, clockwise moment is the positive yawing moment. Okay, so that is considered positive yawing moment. Then relative velocity on the right is called positive side slip angle. This we've seen before. So if this is your fuselage reference line and you have V infinity, so this velocity is on the right of your fuselage reference line. So this is positive beta. Now if it were on the left, this would be negative beta. Okay. Okay. Then as far as control surface deflection, deflecting the elevator to the left is considered positive deflection of rudder. So if this is your fuselage reference line, and if you deflect your elevator like this, okay, now which direction would it produce a force in? This is positive delta R. So which direction would it produce a force if I deflect my rudder to the left? Negative yaw. Okay, yeah, negative yaw, but force in which direction? Yes, it will produce a negative yaw. So you have minus Cn. Force would be right side. Okay, yeah. So it will be this. And that force is denoted, side force denoted by Y. Is it positive or negative? Will it be positive side force, negative side force if I deflect my rudder to the left? You're right. It produces a force on the right side. Is that positive or negative? Negative, right? It produces a negative side force, correct? So, oops. Is it negative Y? This is the minute. Is the slide not refreshed? Yeah. So that is the positive Y axis, right? Positive Y. This is the positive Y axis. This right wing is the positive Y axis. So deflecting the rudder towards the left will give you a positive side force. Okay. Okay. Now for static directional stability. So if your aircraft is encountering a positive beta, you need to reduce that. So you need to get rid of this. So if this was your aircraft and it's facing a positive beta, you need to yaw your aircraft in order to make this beta zero, right? You need to negate the effects of this positive beta. So for that, you need to yaw your aircraft towards the beta, right? So for a positive beta, what should your yawing moment, restoring moment be? Positive, right? So dCn by d beta should be positive. So your inherent tendency to go back to equilibrium is given by the fact that your C and beta should be positive. In our longitudinal stability, it was Cm alpha should be negative. Here it is C and beta should be positive. So this is the only condition for directional stability. Okay, in longitudinal stability, it was Cm alpha should be less than 0. Okay, yeah. So now let's just see. So this sentence says that the induced positive beta produces negative side force. Why? So if this was your fuselage reference line, you have beta here. This is positive beta. It produces a force in this direction, right? So your tail sees an increase in angle of attack. This was your tail, and it produces a force here. And this is negative y. So your Cy beta will be negative. For a positive gust angle, positive side slip angle beta, it produces a negative side force. So Cy beta is negative. So this is just the final equation for C and beta. This is a revision of the stability control course. We have derived this. And the reasoning for why there's a negative sign here is because your Cy beta is negative. Now, what are the components that contribute towards directional stability? Vertical tail, yes. For longitudinal stability, you had your horizontal tail. For directional stability, you have your vertical tail. So vertical tail contributes towards a positive C and beta, which is what we need. Similarly, a swept wing produces a positive C and beta. Why? Because there is a differential drag. Just like the previous case, there's a differential drag. The induced positive beta makes sure that the drag on the right wing also increases. So it produces a restoring moment. Okay. So C and beta positive is from the vertical tail and from a swept back wing. These two structures give you a required stability, directional stability. Now going to the control aspects for positive rudder deflection. That is, we just discussed this. So if I deflect the rudder towards the left, so positive delta R, that is left, gives you positive Y and gives you negative Cn. It's a negative yawing moment, right? If I deflect my elevator, if I deflect my rudder this way, produces Y, produces a negative Cn. Okay, so your Cn delta R will be less than 0. Okay, now just the comparison between the longitudinal and the directional case. For static stability, longitudinal case, Cm alpha was, you needed to be less than 0, only condition. For a directional case, C and beta should be greater than 0. Now for trim, to trim the angle, trim the aircraft at positive angles of attack, you required your Cm not to be greater than 0. This was not a mandatory condition. It was just for, because we prefer to trim it at positive angles of attack. Similarly, for directional stability, you have Cn naught. Like Cm naught, you have Cn naught here. But since your vertical tail, your rudder, they're all symmetric airfoils, beta, you usually trim at beta equal to 0. You don't trim at positive beta. So for that, Cn naught is usually 0. Okay. Now coming to the control, Cm delta E. So for a positive deflection of the elevator, it produces a negative pitching moment, right? It pitches down. If I deflect the elevator down, it produces pitch down. Similarly, if I deflect the rudder left, it produces negative yawing moment. So Cm delta E is less than 0 for longitudinal case and Cn delta R is less than 0 for directional case as far as control is concerned. Okay. Now let's move on to lateral stability and control. What are the conventions in this case? Right wing down is considered positive roll. Again, just see your, if you take your aircraft, this is your positive x-axis. Place your thumb along the positive x-axis and see that the right wing going down is a positive roll, right? So that is how, that's the convention that we follow. Then right aileron up, left aileron down is considered positive rolling moment. So if this is my aircraft and this is the right wing, this is the left wing. If I deflect my right aileron up, the lift on right wing will increase or decrease. Decrease. So if I show small lift and left will increase, the lift on the left wing will increase. So it will produce a positive rolling moment. So right wing going down is positive rolling moment. If I deflect my right aileron up and left aileron down, it produces this same positive rolling moment. Okay. Now for static lateral stability, the only condition is that CL beta should be less than 0. Okay, so when you have a positive beta, there is a y force, side force generated on the vertical tail, and the vertical tail is above your CG. So will this produce a positive or negative rolling moment? So if I see from the back, something like this, produces a side force here, right? And CG is obviously somewhere along the fuselage. So will this produce a positive or negative rolling moment? Just try looking at it again. So it produces this moment, right? And this is from the back. So this is your vertical tail. So it produces right wing going down is positive roll. Is this moment right wing going down? Negative, correct. So that is why your CL beta is negative. Okay. Okay. So yeah, what are the components that contribute towards this vertical tail? CL beta is negative. We just saw that. For a high wing configuration, your CL beta is negative. And if it's a low wing with a dihedral contributes towards CL beta negative. So these are the components that contribute towards lateral stability. Okay. Now, okay. So I think we're done with the contents of this week. So we'll just, previous class we had seen how to calculate the aerodynamic center. Now let's see how to calculate the neutral point. So this is simple wing and tail configuration, and the quantities given to you are the X from a reference point. We are taking the reference point as the leading edge of the wing. From that point, they've given you the location of the aerodynamic center of the wing, location of CG, location of neutral point, and location of aerodynamic center of tail. What we need to do here is find this quantity. How do we start this? How do we start deriving this? So is this configuration stable or unstable? Is this wing tail configuration? This is just the view of the fuselage reference line. Is this configuration stable or unstable? Stable. Why is it stable? CG ahead of neutral point. So what is the static margin here? XNP minus XCG, and it's positive, right? So it's, yeah, it's correct. XNP minus XCG, and it is greater than 0. So for a stable aircraft, static margin is greater than 0. This is just like we had seen. Okay. So now, how do we proceed with the neutral point calculation? Let's just do the derivation together, but tell me how to proceed. How do I start? I think this simple configuration we had done, like it's the basic derivation that we do in the stability control course in every introductory course, right? So how do we start deriving this? To find out the neutral point. XNP, we need to find out XNP. How do we start? We'll do the derivation together, but just tell me where to start. maybe refer your stability control notes or again, Google it and just tell me how to start. Okay. Slope of CM and CL is 0 at neutral point. Yes. So how do we start the derivation? Finally, we need x and p equal to some terms, right? From the terms that are given to you in the diagram. So how do we start? You're right. Slope of CM and CL is 0 at neutral point. Correct. So with what equation do we start? CM alpha of the aircraft. I don't know. It's not that. You start with the CM, right? Let's start with the moment. Forget CM. Let's start with the moment. So it's easier to write the moment, right? So let's start with that. Where do I write it? Okay. M at CG, moment at CG. What is the moment at CG? Just take this to be a cambered airfoil and this to be symmetric airfoil, okay? So now tell me, what is the moment at CG? Several terms will contribute towards the moment at CG, right? So what are those terms? Okay. Just take a minute or two and write down just this first equation, moment at CG, using the various forces and the moments that you can think of acting on this configuration, simple wingtail configuration. Okay, just take a few minutes and write it down and then we'll do the derivation. Okay. Okay, let's start with it. So, I said that the wing was a cambered airfoil and tail is a symmetric airfoil. Okay, so let's just start at the lift at the wing. So you have lift on the wing and the lift on the tail. Okay, so let's start. So moment produced by that wing lift would be on the wing, and what is the distance between the aerodynamic center of the wing and CG? So it will be XCG minus XAC wing. So force into the distance. Plus, it's a cambered airfoil, so it has a moment, right? So that MAC wing. So you have an MAC wing that will also be transferred to CG. Then let's move on to the tail. So what will that produce? Minus. It's a negative, it's a pitch down moment, right? So lift at the tail into, what is the distance here? It will be XAC tail minus XCG. Okay. Now these are in terms of moment. So we need to non-dimensionalize it. What do we do there? Do we do for that? What can be done? How do we non-dimensionalize this? Divided by half rho v square SC. So divide, there is that. Divide by half rho v square SC bar. So what do you get? You get, so before that, let's just try expanding this. Okay, let's just try expanding it before that. So it makes it easier. Okay, so let's just do MCG. So the lift on the wing has, how do you expand lift on the wing? LW. Half rho v square SCL wing XCG minus XAC wing plus, what will it be here? MAC wing minus half rho v square S. Here it is ST, right? It's the tail. So it's the area of the tail. ST CL tail into XAC tail minus XCG. Okay. Now you divide on both sides by half rho v square SC. So it makes it easier. So you do divide by rho v square SCL. Oh, oops. C. And C bar. Okay. Divide on both sides by the same quantity. What do you get? You get CMCG. So we can just write it CM. Hereafter we'll refer to it as CM. Is what comes here. You get CL wing by XCG minus XAC wing by C bar. Here it will be what? It will just be, it's divided on this by the same quantity. So it will be CMAC wing. Right? Here what will it be? Minus, this is also VT. Okay, it's also VT. So what will it be? Here it will be minus VT square. You're dividing it by V square. V square. Here it will be ST upon S. CL tail. And the distance is same. XAC tail minus XCG by C bar. Anything left? No. Okay. So when it's divided by C bar will just represent it by an overhead bar. Okay, so it will just be X bar CG, X bar ACW. Now we need to expand this CL of the wing. So it's a cambered airfoil. How will we expand that? So CM, CL of the wing is CL naught plus CL alpha into alpha. So it is CL naught plus CL alpha into alpha, right? CL alpha wing into alpha wing X bar CG minus X bar AC wing, right? So what will this be? This will remain the same. CM AC wing minus VT square by V square. It's represented by the efficiency factor. So just write eta T, then ST upon S. CL tail, how do you expand that? It said that the tail was a symmetric airfoil. How will we expand that? So CL tail would be CL tail would be so CL tail, CL naught will not like is a symmetric airfoil, right? So there won't be any CL naught. So it'll just be CL alpha into alpha, correct? So CL alpha tail into alpha tail, alpha tail. Let's write that clearly. Into alpha tail. The distance is same, so it's X bar AC tail minus X bar CG. Have we missed any term? No. Okay. So now we need to expand this further. So what is alpha tail? We need to get it in terms of, so your CM is CM naught plus CM alpha into alpha. Right? We need to get it in terms of this. And this alpha is alpha wing. So now we have terms that are dependent on alpha wing and terms that are independent of alpha wing. Before that, we need to expand this alpha tail. Alpha tail is another term that is dependent on alpha wing. So what is alpha tail? How do you expand it? What is alpha tail? Is alpha tail same as alpha wing?
So wing setting angle of wing minus setting angle of tail.
Okay, in this case, there is no setting angle of wing. So it's just, is it just minus setting angle of tail?
Downwash.
It's plus or minus downwash. So here it will be plus, right? So it's alpha wing plus IT minus downwash. So the wing tail setting angle here in this case, it's set at a positive angle. So it will be plus, right? Now what is this downwash? How do you expand that? How do you expand the downwash? Again, you have a term that is independent of angle of attack of the wing and one that's dependent on it. So you just simple linear expansion plus dou epsilon by dou alpha wing into alpha wing. Now we need to substitute all of these parameters here into this quantity. And then you will have CM naught and CM alpha. So let's do that. So your CM would be, what was the equation? Okay. Let's just try doing it. So it will be CL naught plus CL alpha in alpha wing. alpha wing. This was x bar CG minus x bar AC of the wing plus CMAC wing. And you had minus eta tail S tail upon S CL alpha tail. And here you will have alpha wing plus tail setting angle minus epsilon naught minus dou epsilon by dou alpha wing into alpha wing, the whole thing into x bar AC tail minus x bar CG. Okay, so now you can write terms that are dependent or independent of angle of attack. So let's just find out CM naught first. CM naught. What would be what all terms would come in there? Terms that are independent. Okay, let me take another color. So this whole thing. So all of these terms would come under CM naught. So that will be CL naught into x bar CG minus x bar AC wing plus CMAC of the wing minus eta tail S tail upon S CL alpha tail into IT minus epsilon naught into x bar AC tail minus x bar CG. Have I missed any term? Let's check the whole thing again. All right. So now let's find out CM alpha. The remaining terms, right? Again, let's take another color. This, and this. The terms that are excluding the, depend on angle of attack. Okay, so it will be CL alpha into x bar CG minus x bar AC wing minus eta tail S tail upon S CL alpha tail into 1 minus dou epsilon by dou alpha wing into the distance x bar AC tail minus x bar CG. Again, are we missing any terms? I don't think so. So let's proceed. No other terms, right? All done. Okay. Now, how do we find out neutral point? Now that we have the equation for CM, you had mentioned initially, it's the point where CM alpha becomes 0, right? So, oops. So, at CG equal to neutral point. So, at neutral point, here CM alpha becomes 0. So, just substitute these quantities into CM alpha, this equation, and you can find out neutral point. Can you try doing that? Just try doing that. So in place of XCG, you will write XNP. And wherever you get CM alpha, you put 0. Let's just do it. In that equation, Cm alpha is 0. So 0 equals Cl alpha into x bar np minus x bar AC wing minus eta tail st upon s Cl alpha tail 1 minus dou epsilon by dou alpha wing x bar AC tail minus x bar neutral point. Now just rearrange these quantities and what is the value? What is the equation for x bar np? Is equal to, just try doing it. Just rearrange the terms and just tell me what x bar np is equal to. Try doing it. Just do it. So it will be Cl alpha of the wing. Okay, so I think I have been skipping that. Cl alpha of the wing. Everywhere it's that, okay, it's wing. Subscript. Yeah. So this is Cl alpha of the wing into x bar AC wing plus eta tail st upon s Cl alpha of the tail. We have 1 minus dou epsilon by dou alpha wing into x bar AC tail divided by Cl alpha of the wing plus eta tail st upon s Cl alpha of the tail 1 minus dou epsilon by dou alpha wing. Is this the formula? Can you verify? Am I missing something? Just see if I'm missing a few terms or if anything sign is different or is there any mistake? Okay, so let's just rewrite that and then we'll try to, okay, so it will be something x bar np is Cl alpha of the wing into x bar AC of the wing plus eta tail st upon s Cl alpha of the tail 1 minus dou epsilon by dou alpha wing x bar AC of the tail divided by Cl alpha of the wing plus eta tail st upon s Cl alpha tail 1 minus dou epsilon by dou alpha wing. Okay, so this is the formula for neutral point. Okay, so now just look at this equation, see the pattern it follows. What it is it's like a weighted average. The neutral point is the weighted average of the aerodynamic centers, right? So how do you define the aerodynamic center and neutral point? They are the same definition. So neutral point is nothing but the aerodynamic center of the entire aircraft. Okay, so neutral point would be the weighted average of the aerodynamic centers of the various aerodynamic components. In this case, there is one wing and there's one tail. So it's the weighted average of these two components. What I mean by weighted average is like, so it's some weight assigned to x bar AC wing plus weight to x bar AC tail by W1 plus W2. So you do find out the CG of CG of like combined bodies or the moment of inertia. Like you have weighted averaging happening, right? CG, not moment of inertia, CG. So this is something that is following the similar trend. So what it does is that it is the weighted average of the various aerodynamic components. Okay, so now if I were to add one tail, so what would it be? You would get third weight plus x bar AC tail 2. If you have like two tails, you get that. And here it will be weight 3, right? And what would this individual, so okay, if I add a canard, so it will be W4 x bar AC canard plus W4. And in this case, W4 would be, so eta tail, that will not be there, that it will not be there for the canard because it's ahead of the surface. So it will be area of the canard by area of the wing, CL alpha of the canard. And this downwash component will not be present in the case of canard. So this will be the weight 4, right? Are you able to appreciate the fact that it's just a weighted average of the various aerodynamic components of the aircraft? So now if you add another wing or add another tail or add a canard or add any other aerodynamic surface, the neutral point calculation would just be a weighted average. And what would the weight be? It would comprise of these quantities. It is comprise the quantities that like CL alpha of the tail, CL alpha of the wing, plus some other terms. Surface area of the wing, surface area of the tail, those would come. Okay. So now let's see another composition. Look at this. So it says the neutral point calculation of this configuration. Here you have a canard. Oops. So this is a canard. You have two wings, wing 1, wing 2, and you have a tail with a negative tail setting angle. Okay. And then they've given you some other parameters. Let's not look at the table for now. Let's just try finding out the neutral point location. And then we'll put in numerical values and then find out the actual quantity, actual value of x bar and p. Okay. So let's try, or I think you can try doing this by yourself. Find x bar and p. You don't have to find out the actual quantity, actual numerical value, just the expression. Okay, so you can follow the same process that we did before. Find out first would be what? You write let me just write it down. You would have, yeah. So these are the quantities given to you, okay? So XAC wing, XCG, XNP, XAC tail, XAC of the canard. So these quantities are defined. They're not given to you. These are defined. And then you find your expression for XNP in terms of these quantities. Okay, just like the previous case. But you have some extra structures here. How do you proceed? First, you start with MCG. Write the equation. So lift on the wing into the distance, lift on the tail into the distance, lift on the canard into the distance. Then divide by, so this is first step, then you divide by half rho v square SC bar. Okay, next step, expand CL equals CL naught plus CL alpha into alpha. Not just for the wing, for all the cases. So I'm just writing the general thing. Okay. Plus CL alpha into alpha. Then your CM equation is CM naught plus CM alpha into alpha. You need to get it into this form. So now what do? You'll have to find out alpha tail alpha canard. All right. Find out these two, substitute in this equation. Then you find out Cm naught, then Cm alpha. Then what do you do? X bar Cg equal to X bar Np and Cm alpha equal to 0. In this equation, substitute these quantities and you can find out X bar Np. And then see if what we had seen before is true, if it's a weighted average of all the aerodynamic components. Okay, try doing this and we'll solve this together next class along with the numerical values. Okay, just try finding out this X bar Np formula. Start with moment, divide by half rho v square as C bar, expand the CL, find out Cm naught, Cm alpha. Before that, find out the angle of attack at the tail, at the canard, and then substitute that Cm alpha is 0 at neutral point. Okay? Okay. So do this and we'll try doing it together in the next class along with the numerical values. Okay. Do you have any questions, any doubts from today's session? If not, we'll end the session here. We'll meet again next Tuesday. All the very best for your assignment.